Hi, everyone. I was telling one of my colleagues, when I organize this kind of sessions, I always get scared about the first speaker, the speaker before the break, and after the break. So at this point, I'm the victim here. My session is after the break. But I think it's a very good crowd today. Not much as yesterday I expected, but still a kind of a decent crowd. So thanks all of you for joining. So this session, so my name is Anirban Bandyopadhyay. I am from Global Foundries based in Santa Clara. I head the strategic applications in the end market organization. I'll be moderating the panel. And the topic of our discussion today is hardware technologies for future wireless. So I will start just to give a kind of a context, and then I will invite my esteemed colleagues, the panelists here. And the way we are planning it here is we'll give opportunity to all the panelists to give their view very briefly, and then rest of the session will be interactive with the question answers. So from yesterday onwards, you guys have seen a lot of discussions of the applications, standards, network, systems, and all those things, right? What's happened today, what is going to happen in the next 10 years and others, right? So again, it's not meant to be very comprehensive, but what we are trying to show here is all the different cellular standards like cellular communications, Wi-Fi, satellite communication, Bluetooth, and others is going to be kind of migrating to the new generations, right? 5G to 6G, Wi-Fi 7, 8, SATCOM going to support 6G and all those things. And also you heard a lot of things like this multi-gigabit per second data rate requirement, zero coverage whole network, power efficiency has been talked about in multiple sessions, and also the intelligent connectivity, right, including smart sensors. So all these things have been talked about. But what hasn't been talked about so far is what hardware innovations are needed to address those. So this session is particularly focused on that topic, okay? With that, I will basically invite my distinguished colleagues who are the panelists here. Please join and be there. Yeah. Yeah, if you go in the order, it will be Gary here next to you.
It's a memory test.
Yeah.
It wasn't up there long.
It's okay.
I think roughly, right? Right. I remember it was next to you.
Yeah, I was on the end.
Okay, so first I will invite my panelists to come one by one to introduce themselves and briefly talk about what's their view on this topic, particularly the hardware innovations part of it. So I'll start with Gary. Can you please introduce yourself and then take your slides?
Yeah, thanks, Anirban. My name is Gary Xu, and I'm from Samsung Research America, and I lead the 6G research team over there. What I'm going to talk about today quickly is about our vision and the hardware technology related to 6G. So as I mentioned in the panel yesterday, we have a new way of thinking about what 6G would be. Instead of focusing on the traditional KPIs such as data rate, latency, we are looking at those new attributes such as AI, sustainability, coverage, and security. So related to the hardware technology, I want to talk about the sustainable network and ubiquitous coverage mainly today. So for the energy efficiency, this is actually one of the main concerns from our operator customers, not just for the electricity kind of cost, but also for the heating size of the base station that actually has a major impact in terms of the installation cost. So improving the energy efficiency can help on those aspects. And we are actually looking at the supply modulation for the high efficiency PA so that we can improve the efficiency during the peak operation and back off. And also there are new GaN on silicon type of devices and other GaN devices which actually can help reduce the cost and improve the efficiency. And for the coverage, we're looking at this distributed MIMO technology, which can use the joint coherent beamforming to improve the coverage for FR1, especially for the sub 1 gigahertz frequency. And for the millimeter wave, we want to use this joint phase and the timer, right? JPTA technology to fundamentally improve the coverage of millimeter wave system. You know, actually the current FR2 millimeter wave 5G system is not very successful, mainly due to this coverage issue. So using this JPTA technology can create a multi-beam pattern so that we can support multiple users at the same time from the base station. And for the FR3, we also want to make sure the coverage is taken care of at the very beginning of the system design so that we actually can have sufficient ERRP and the coverage for the higher frequency band that's comparable to FR1. So those are the things I want to talk about. Yeah, thanks.
Thank you, Gary. Next, I'll invite Chidi. Can you please come and introduce yourself?
Thank you, Anirban, and thanks to the team for inviting me. It's a pleasure to be here. My name is Chidi Chidambaram. I kind of manage everything on silicon and package that happens at Qualcomm, all the way from 2 nanometer leading edge CMOS technology to 0.25 power management. And in the middle of that, there's a lot of RF chips we do. Unlike everything else being silicon in RF, we got all the alphabets that we deal with, from GaN and GaAs and passives. So it's much more fun. There's a lot more physics in the RF area. Being at Qualcomm and being at the place where I get to kind of look at every chip that goes out, I can see a lot of potential that is actually doable in the lab and measurable on data. But when you look at what people are able to take advantage of the wireless today, it's very limited, in terms of what's available to people in the open. And I know there's a lot of reasons why, of course, right? But I want to kind of center on the reliability as the key aspect. And it'll also drive into what I think is a key pivot we have to take with AI coming into this field, how we're going to, hardware systems have to leverage AI to improve reliability. That's kind of the topic I kind of want to broadly address, right? So if you look at the spaces in which we are, like personal devices, cell phones or XR, the adoption of the Gs have always been, non-linear, right? The technology comes at an even cadence and the capability comes at an even cadence, but the acceptance and the adoption is largely driven by user experience. And that comes from applications that make the user experience possible. So from 2G to 3G was a kind of a slow transition because even though we could do a lot of data rates, the smartphone wasn't ready at that time. So it kind of waited till 4G for that to take off. So I think the similar thing is happening with the millimeter wave. We are getting a very good adoption at the sub-6, but the millimeter wave is waiting for that killer application. And I think that killer application is got to do a lot with network reliability and how we are going to make this seamlessness happen. You got too many different wireless standards. There is Wi-Fi, there is 5G, 6G, millimeter wave, Bluetooth. In the end, everything is going to become, 10 years from now, we probably won't call a smartphone. It'll be a smart assistant. The phone aspect of it will be very less important compared to the other things it can do. And in order to get there is going to be a lot of seamlessness in these networks that we have to build and reliability that has to come there. So this is true in every field, right? Like if you take industrial automation, there's a lot of private networks there and there is a lot of robotics in the industry, but the adoption of the wireless is not to the extent that the technology is capable of, because they cannot guarantee everything is going to happen on schedule, on the pace. So there's, again, a lot of this reliability that's kind of stopping the user experience from being realized. And you take auto, right? Human safety is probably the biggest thing that wireless can enable, and it can, but everything has to be present. There has to be a roadside unit that can guarantee a latency and connection density that's always going to exist. today in the implementations, these are very spotty and there are not, even when they designate a smart city and implement for that, it's still kind of spotty. So I think those are the opportunities for us in hardware to try to solve. And I think AI is going to be a critical play in this. So if I look at AI adoption, the digital people are much closer to what's happening with the AI, and they are kind of absorbing the concepts into helping the productivity in those. Like, there is digital design, place and route. They are taking these concepts. But when I look at RF, I think the RF people are fundamentally not as plugged into what's going on with the AI. I think that's the biggest opportunity for us. Because once you make the systems close looped, like today, the transceiver is kind of a one side talking to the RF front end. There is no feedback. For AI to be effective, we got to create these loops instead of one side transmissions. So if the hardware systems think about trying to get these loops enabled, then we can help AI to solve the reliability problem that we have. That's kind of the big picture message. Be looking forward to the discussion. Thank you.
Thank you, Didi. Next, I'll invite Julio. Please introduce yourself.
Hello, I am Julio Costa, Vice President of RF Technology Development at Global Foundries. Let's see, today, the slides here. Okay. In my role, I basically am responsible for the technology roadmap and making decisions and strategies that will address our future customers and our future customers' needs. So we're kind of in a very interesting point in our roadmap because we are, as you know, if you're not familiar with Global Foundries, we have solutions in bulk CMOS, in FinFET at 12 nanometer, fully depleted SOI technologies, which is really one of the areas that Global Foundry pioneered, along with RF SOI as well. And as well as in silicon germanium, another pioneering technology that Global Foundries, IBM developed in the prior decades, which are now in full deployment. And more recently, gallium nitride on silicon, which is an effort that we started a couple years ago, again, vying for this future industry solutions that we think are going to be necessary to address this market. So in the food chain for AI, we are in a different platform because we're not a 3 nanometer, 5 nanometer, 7 nanometer fab. Our capability stops at 12 nanometers. So we are sort of handling the RF on the edge, handling sort of these necessary building blocks that you have. And we are making bets on what is it that this industry is going to need. So this is a really good time for you to address us and what kind of building blocks, what basic bricks do you need that we are currently not addressing. So our best choices today, our best guesses, I would say, are that we do need, of course, at the end, you still need efficiency in your PAs, you need good LNA characteristics, you want to dissipate less power. So all those things are very obvious to us and what you need to do. But is there something else in terms of power, voltage handling, in terms of sensing, future, do we need more low-cost silicon phase arrays? What is it that industry, this market needs that we're not currently doing? So our bets are really, like I said, in terms of SoCs, highly complex SoCs, the 12 nanometer or above are going to be sufficient for this edge area where we're at. And that integrating certain elements, like, for example, silicon germanium into FDX technologies, which will give us, say, 500, 600 gigahertz FT capabilities, will be necessary for this next tier of performance that we expect, as well as much lower power consumption in, for example, building blocks like LNAs and power amplifiers, and hence our bets on a advanced silicon germanium platform, as well as gallium nitride on silicon. We are making a bet also on gallium nitride on silicon at lower voltages. Traditionally, this is a technology for 28 volts and above. And we are seeing good enough results to where we think that this industry could really benefit from a 5-volt solution for a handset type of PA voltage solution for gallium nitride. So we are, again, those are sort of our options. But one thing that we are investing as well, and you're going to see more and more of this from Global Foundries, is in this 3D IC concept, this heterogeneous integration. It's very difficult to integrate these silicon germanium devices, gallium nitride devices, always as part of a 2D offering, because also you get very complex mask sets and things that take 6 months to process. We envision 3D ICs being a very much part of the next decade, a very important building block where we are bringing different wafers with different capabilities, bonding them together and providing a design environment that allows you to design in this 3D concept. So bringing solutions together that otherwise would require separate ICs, would require separate environments. So how to do that and how to release it, obviously there's a cost there. We have to create the enabling solutions, the tool sets that will allow you to design with that. And we're kind of in that transition. So we're in a unique time where you can guide us into what is necessary. Are these the right building blocks? What kind of multiple technology flavors should we see integrated? A SiGe with FDX or a sensor type of thing, or gallium nitride into, for example, a advanced CMOS. This is where we're at right now. And you're going to hear a lot of different insights from us. I would love to get your take on this roadmap that we have proposed. So thank you.
Thank you. Patrick, please introduce yourself. Yeah, this is the key.
Sure. Okay, I'm going to start with who knows Soitec? Show of hands. Okay, very few. So we're the material provider, but a very key one, for the RF related applications or in all the cell phone related products today. So the highlight, for us is we kind of operate in the box that's in the center of the screen. We get inputs, performance, power, area, cost, time, from our customers and our customer's customer. And that helps us, fuel our innovation. And so innovation for us is, we don't build the substrate from bulk, but we buy bulk and we use our bonding technology and our cutting technology to form what we call an engineered wafer. So we can do crystal on dielectric, we can do crystal on amorphous type materials, things that you can't historically get, from a pure wafer type standpoint. That has a lot of benefit, and and the attributes that we are fed, basically allow us to engineer a wafer that is illustrative of what the application drivers are. And so I show that kind of in the right side of the slide. Where our RF related front end technologies are deployed for temperature tolerance, related applications, with a different material play. Very analogous to what we would do for a conventional, but, taking out harmonic distortion related, requirements, to a temperature regime that's not normally adhered to in our substrate evolution. So that's what we do. And we have a materials library basically that we go through, a Rolodex more or less to put these things together. How that feeds into the technology-related drivers. Some of my colleagues mentioned this. Extensions of existing technologies, fully depleted SOI, tighter controls, to top silicon roughness. All these things drive, variability-related signatures. The deployment of that related capability is ongoing. As Giulio mentioned, FTF Max, getting to a higher frequency-related application as a substrate-related deliverable that we could enable. Piezoelectric on material, for on insulator for filter. I would say some of the disruptive technologies, like 6G indium phosphide is interesting, 4-inch. Type substrates, but can we make them in a bigger form factor? Again, the process-related technologies that you can get at 6-inch or 8-inch or 300 millimeter are much broader if we can do that. And then we have to balance whether there's a cost-related impact for that. And certainly GaN is another one. Gary highlighted GaN. It's FR3 is a real big application space for RF. There's also power GaN. Related requirements there. And I'd say in the last one is the 3D packaging is really an interesting space, from a material supplier type perspective. Again, the form factor of your phone doesn't necessarily change, but the complexity built in the phone does change. And so, getting creative on the packaging related, things, could be very interesting in this space. And I always say it's like, as a material supplier, one of the challenges that we have is we kind of need the connectivity, across the enterprise, basically to get the feedback, because thinner is, less thermal or more thermal, related constraints. And you have the attributes of, a flip chip type bonded, substrate that's, floating, and the electrical signatures are different, between the different applications. And so any systematic error that can be fed back in the substrate allows us to innovate, and differentiate, that space. So that's my 2 bits. Thank you.
So, Patrick did an excellent job in introducing his company. Didn't talk about himself. He is the senior director of the field technology covering all North America, and we know him very well. Thank you, Patrick. Gabriel.
Hello, I'm Gabriel Reveiz. I'm a professor at UCSD, and my group does hardware. So we deliver a lot of hardware. And I'm always interested and think like what makes a good hardware engineer. And so I'm going to show you a couple of slides of what I think makes a good hardware engineer. So that's a hardware engineer. First of all, you gotta be a crocodile. You have to have a very hard skin and a thick skin because you are going to fail a lot. And it's like, I call the software people softies. Like, you do a mistake, you say, oh, let me go change few lines of code of MATLAB code, and then you do another mistake, you change few lines of MATLAB code. It's like tissue paper. They're like softies, basically. But the hardware guys, these are the T-Rexes. These are like you gotta be on the apex predator here because mistakes are very, very costly. And you have to train in this mentality. You have to train that you have to have attention to detail, and you have to be fearless, and you have to attack a problem, and you have to know antennas and packaging and chips and this and that. I mean, if you saw our posters yesterday, we're building 1 meter by 1 meter reflect arrays at 3 to 6 gigahertz with true time delay. We're building with Samsung and Qualcomm, we're building 2 times 48 gigabit per second, 64 element VH phase arrays at 140 gigahertz. I mean, you need guts, you need huevos, you need balls to do this stuff. And you need, so all of this, I mean, you gotta have this mentality. And I train my students to be like this. I mean, I train my students to be really fearless. And my best interpretation of a graduate student is this one. Okay? It's this one. I mean, there is so much in this. First of all, they look like graduate students, number one. First of all, they all look like, they dress like graduate students and so on. But if you have seen the movie Braveheart, these Scottish people are attacking the well-armed, well-trained British army. And they are a bunch of renegades. And you know what? And they attack. And they are fearless. And that is what, in my opinion, makes a great graduate student. It's like, this is a problem. Nobody can deal with this problem. You are going to spend 3 years and you're going to attack this problem and you're going to solve it. And, in 2000, I remember going to Tim Hancock, who became a DARPA PM and this and that. And I said, Tim, SIGI is coming, SATCOM is coming, you're going to build a phase shifter. And he said, what? He said, yes, we're going to build phase shifters and SATCOM systems in SIGI in the year 2000. In the year 1991, I go to Walid Ali Ahmed, who's now at Apple, and I say, Walid, we're going to build receivers at 94 gigahertz with 6 dB noise figure. He said, what? I don't even know what is a receiver. That was 32 years ago. SATCOM, we were doing SATCOM before SATCOM was there. 10, 15 years ago, we were building phase arrays and 256 element phase arrays and 1024 element phase arrays, and they were oscillating and they were not working and they were expensive, but we kept on doing it and kept on attacking the English army and so on and so forth, fearless. And then, we succeeded. So really, it's a mentality that you cannot be afraid of anything and you can do everything and you have to conquer obstacles. And then you become a good hardware person. And that's how I train my students. Thank you. By the way, I am there, this guy here with the colored face there. Yeah, yes, that's me there, exactly. That's.
Thank you, Gabriel. So what we'll do now, we'll have the question answer session. So I'll start with some questions to my panelists, and then probably I will make it open to the floor, and you can ask any questions you want to my distinguished panelists here. So let me start. My first question would be probably, most of you are thinking about it anyway, right? Because from yesterday onwards, we are talking about AI, right? AI. I don't know any session we didn't touch upon AI. The question to my panelists would be, what the impact of AI, let's say it comes to the edge, whether it's the base stations, or smartphones, laptops, and other places, what is the impact on the radio architecture, or particularly RF technologies? Maybe Chidi, you want to start?
Sure. I think I kind of addressed it a little bit in my opening talk. I feel like the AI is got to help what we need the radio systems to do, right? That's one aspect. There's also the demand aspect, right? From the demand aspect, I think AI is going to drive a lot of wireless connectivity, right? So if you think about your phone becoming a personal assistant and your personal assistant becoming a robot, they're all going to need wireless access to do everything. So from the demand side, AI is going to drive a lot more wireless requirement. But I see as a hardware engineer, right, the T-Rexes, we got to face the challenge. I see AI providing a key solution to our problem, where today the complexity of so many different networks and so many, I got to build a phone that works in every country, and it has so many different channels. There's it's not always guaranteed what's available. It's spending power on trying to read signals on things that don't exist. There is a lot of this type of redundancy, and our budget is taken over for things that are not currently needed, and AI can really help solve this problem. But we got to get it into our system. And the first thing we need to do is to let a centrally stationed AI, probably on the digital side of the chip, to be able to manage this whole thing and make decisions on the fly. For that, we need to make the system closed loop, right? Today, it's kind of, most of RF is one-sided. Like, transceiver goes to RF front end, goes to the antenna, goes to the receiver. We need to kind of create a closed loop so AI can start playing a role in helping us do what we need to do.
Thank you, Chidi. Anybody who wants to add something to this?
One area I think AI can help is, again, to improve the energy efficiency, right? So for example, how to improve the PA efficiency using AI as a tool. So one conventional tool is a DPD, digital pre-distortion, right? But this type of solution has been around for many years, but our system has become more complex and PA has become more complex. So it's actually possible to use AI, the neural network, as a tool to deal with such kind of very complex problem, and also deal with the additional kind of parameters in the transmitter, so that the performance can be improved and the complexity of the DPD algorithm can be reduced. So that's actually an area I think definitely AI can help.
That's a good comment, yes. Anybody else wants to add anything to that?
Well, I would just say, like I said, we always see we have to provide solutions that have better efficiency, good low noise capability, and now we see AI, on the edge, driving us to incorporate different bands, different areas where currently our technologies are challenged. So this will drive us to investigate how do we get better PA efficiencies at higher frequencies, at wider channels, and this is kind of why we're looking at multiple technologies to address those issues, because that's going to start there. We have to provide. At the end of the day, you're still a wireless system. You still got to send power and you got to receive power in a certain way. So that's essentially where we see AI driving future needs for us. In terms of data rates and PA solutions and LNA solutions.
Yeah, Gabriel.
I I don't want to call it AI because for me it is just good software. And I wish I call more deterministic software. For example, for me, if I'm designing a transceiver chip, and some of it was alluded yesterday on this. Well, I want to really concentrate on, for example, the mixer or the synthesizer or something. But if there is a software that can help me do a switch very easily or a layout of an op-amp very easily, especially if I'm doing R&D and a lot what I call the lower level functions doesn't need the SPI very quickly, does some memory, some this and that, and just few lines of code, it will go and lay out and put all of them together. Like, oh, give me an Allen Sallen-Key filter, baseband filter with this and that, and boom, it does it. And where I concentrate on the blocks that really make sense, that, in my opinion, will speed design quite a lot. But I really don't call this AI. I just call it basically good software, good design software, good design. I mean, I don't really need AI for it. It's like I can go to YouTube and find it now. It's just that it's doing it for me more than anything else.
Okay. Let's move to another question. So there are some comments made in some of the earlier sessions yesterday about power efficiency, because people see that's a big challenge going to the future, right? So it's not just the green energy itself, right? So if you think about battery technology hasn't gone up too far. So in order to use a battery operated system, whether it's a smartphone or tablet or any other system, for example, power efficiency is key. So the question to my panelists are, what do you think where these RF technologies will move in order to address this battery efficiency for the future wireless? It can be RF front end, it can be transceiver, but any comment on that? Maybe
it's the PA. That's it. We are so good in RF transceivers. Really, really, it is the PA. Yeah, I mean, maybe a little bit the synthesizer and the LO, delivery, but it's mostly the PA. I mean, better technology, better DPD, better envelope tracking. It is the PA. That's it. Yes. But we have somebody who was born to make PAs. Even his parents called him Peter Asbeck, PA. Yes. Yes. Since he was born, he was called. Since when he was born, they knew that he was going to be the number one PA person. That's why he's called Peter Asbeck, PA. So we have hope for the future.
Yeah, actually, I agree with Gabriel. So if you look at our current base station, especially Massive MIMO base station, has like 32 PAs, 64 PAs. Each one actually burns like many watts of power, actually output like 10 watts of power average. So we actually did the calculation. The PA power consumption by itself actually consumes more than 50% of the power consumption of this entire base station. So the rest of the digital part only consumes the half. Those 32, 64 PAs consumes the other half.
Digital and analog and beam processing and mixers and everything consumes less than half, and then the PA consumes more than half.
More than half, yes. So that's very true, and it's very, very difficult to improve the PA efficiency. I think Peter and other people actually have spent a lot of time trying to improve the efficiency of the PA. But I think right now we already reached very high efficiency, but that's still not sufficient. Of course, using this new device, like a GaN device, I hope we could further improve the efficiency. And also, there is a practical use case because the base station typically does not operate at the peak power. So how to improve the backoff efficiency, that's also important. Right? When your base station transmit like 50% of power, can you still have a very high efficiency? So those are the kind of main challenges.
Okay. Yes,
Yeah. I mean, I think I agree with everything. PA is the most important thing. And, if I look at the commercial systems deployed, today we are not able to use the highest efficiency PA for a given band for many reasons, right? There's insertion loss and there is some chips have to be integrated because you cannot transmit between different blocks unless it's the same chip with the insertion loss issues, right? So I think this is where some of the new technologies that are coming on board, like the 3D, and Julio talked about it, and Mont talked about it. So, but they are not currently at a cost point or integratability point where I can take like gallium nitride, probably going to give me the best PAE, But then I cannot build my system today because my transmit all has to be on a SOI. And if I try to move the signal from here to there, I get so much loss, I can't do it. But with the 3D and the integration technologies that are coming, I think we are going to be able to take the best PA for any given situation and put it together for that purpose and integrate with the rest of the RX system. But it's going to need some cost points, right? Today that's main reason why it's not in production, because it's very expensive. So I think that's why I think Julio is here. He's going to make it cheaper in a couple of years, and you're going to see it soon.
I think you steal my next question. So, Julio, actually, I was thinking about it. So, 3D HI that we are talking about, tell me something about the pros and cons, right? And what we have to do to make it kind of a mainstream.
Yeah, so generally what we call 3D today involves wafer-to-wafer bonding or chiplet-to-wafer bonding. There are two distinct areas, and they're very different types of solutions in a technology side. Foundries like ours will likely focus more on the wafer-to-wafer, and more companies like Qualcomm, for example, could do die-to-wafer. That's a little bit different of a distinction between us, just on the fact of how we deal with things and the practicality of it. Obviously, wafer-to-wafer, you have to bond wafers of similar diameters. You cannot bond a 200 to a 300 millimeter substrate in any kind of cost effectiveness. Today, we have a certain cost structure because basically we're transferring a layer from another substrate to another way, to a host substrate, and essentially getting rid of the old substrate. So all that cost of that substrate that was there just for the transfer sort of goes away. Somehow you have to do all of that. So today, our transfer methods are relatively expensive. We have to start with an SOI substrate. We etch down to a SOI and get rid of it. There are other variations, but they all, in essence, involve that. We have ideas to move past that. That would subtract a very big cost factor. A substrate, Soitec is here. Those substrates are several hundreds of dollars, and we need to figure out how to do that better. How to enable that. That would be a major solution. But yeah, it's a little bit of a chicken and the egg today, where that. We know what in the 3D IC tools, design tools have to be there as well. Does good to have this great 3D concept, but without the supporting PDK that would allow you to do that. And they are also there waiting to see what they're going to do. Do we invest in this area? Where's the business case for it? So we're a bit in this mode right now where we're demonstrating 3D solutions, but cost is a major factor. And we're trying to find ways to take cost out and convince the EDA solutions people to also jump on board and invest really on the next generation technology. There are 3D tools, but RF 3D is not there today. RF 3D is something that has to come later.
Patrick, you want to add something?
Yeah, no, I was just going to iterate. This is why it's important, for somebody like a material supplier to really kind of, work kind of upstream, with the end market, because again, gallium nitride, clear enabling type technologies, that could be, delivered from a substrate provider, and GaN on SOI is not, practically unlimited. We can do that, those type of things. But again, area cost, what makes sense, and if you're going to remove, portions of the material that you don't care about, we have cost models that are built into that, because of the performance-related requirements. So we're using legacy-related technologies, and kind of applications that don't necessarily need that type of capability. So I think it's very important for us, to really, as we look at these disruptions, that are going on, how do we, extract some of the overhead costs that are built into the existing, architecture that can be deployed. To these applications.
So, given the time, I have last question for the panelists, then I'll open to the floor. So, we have been also talking about XR, right? You heard a lot of people talking about AR, VR, lots of things, right? Glasses, headsets, industrial, robotics, and others. And I know Qualcomm is one of the leaders in this field, and there are a lot of good presentation yesterday, the XR capable, the latest Snapdragon as well. Relevant for this discussion, I want to ask Chidi first. What do you think about the wireless technology side to enable this XR to be a kind of a really mainstream and successful kind of an application?
Yeah, I think XR is a perfect or a ideal application for like a 6G type wireless terahertz bands, right? In a phone, it's very hard to see implementation on different buildings, different places, different cities to take advantage of the bandwidth and the latency it provides. Whereas in a very controlled environment like a person using a glass or a XR headset and having multiple devices in the same room or even multiple people interacting on a game, so really high resolution and high bandwidth transmission across these two players playing a game using XR headsets, I think that's probably, in my mind, a more compelling application for terahertz, that a lot of the wireless people are working on all these indium phosphide and really a high bandwidth technology. I feel that's probably the space where you'll probably see adoption and a compelling user experience than even in a true like a cell phone type environment.
Gabriel, you want to add something?
No. I want to talk about university industry.
What about anybody else want to add something to that? Okay. So actually, just one more question for my panelists before I give it to them. I have some for 5 minutes here. So given all these discussions that we had, we have only one person from academics in my panel, right? I want to ask him some questions. Can you share with the audience here how you want to prepare your master's or PhD students given the new requirements coming from the future wireless? Anything that you want to share?
Well, I mean, as I said, it's really complicated building new hardware. And you really have to train them as a mindset. And the mindset is, to be fearless, to go and try the latest, software routines from Keysight and measurements. I mean, there are very few students who feel comfortable using these very complex equipment now and very complex design tools. And it takes time. I mean, that's why you spend 3 years doing a PhD to learn these complex design tools, learn how to build something, learn how to measure something, and not be afraid of failure, and then redo it again and again, and and succeed at the end. It's a mindset. It's more than tool skills too. So it's tools and a mindset. So we train them on that. Also, I would say we are lucky in terms of we are very good partners with certain companies, and they teach us. I mean, Qualcomm, we are very good partners with Qualcomm, Global Foundries. I mean, Global Foundries is giving access to no one except us on the wafer-to-wafer transfer. Samsung, Samsung funds us, Qorvo, ADI, Keysight. Keysight is a great partner with us and shows us all their latest software and so on. And I think the reason why is it's based on trust. They trust us. They trust us because of several things. We take NDAs very seriously. We feed back to them everything that we know very quickly. If we find something that doesn't work, we tell them. I mean, we're not trying to hide anything. It's like all based on full transparency and trust. And at least in my group, we basically have a no patent policy. You can tell, we're not going to patent anything in order to block you or in order to come and try to extract money out of you or sell it to a patent troll who's going to come and sue you 20 years later. We basically are completely neutral on this stuff. And that's why everybody likes to work with us. We are just based on trust and openness, and we show our failures. I mean, I remember two things. One was Jeremy and one was Qorvo. Qorvo asked me to design a beamformer chip and in a certain way, and we did it, and it failed. And we went to the report and we said, look how we did it, and look how there is coupling between the channels, and look how we failed. And I remember Julio said, this is a great outcome. Thank you so much, because now I know how not to design a chip, And this is a fantastic outcome. And we were working with Jeremy and at Qualcomm, and he says, look what we did with our phase shifters, and look how they did not work, and look at the biasing, and look at all of these makes, and we thought it would work, and it did not work. And Jeremy said, well, this is a phenomenal outcome. He says, thank you so much, because now I know how not to do. So I would say, don't be afraid of bad results. Bad results and sharing bad results are as important, if not more important, than good results. Who cares about good results? Who cares about good results? Good results are for softies, Who cares about good results? We want to share the bad results, how you learn the stuff,
Okay, thank you, Gabriel.
Yes.
So let me see, any questions from the audience?
while they're thinking, I have a request to Gabriel. You can leave the AI to the softies, man. we really need the T-Rexes to take the AI, because to do closed loop systems in a complex multi-chip wireless, you cannot rely on a software that is so far away to solve this problem. We got to find a way to create a small model that can reside right in the RF to solve these. I think that's the key for us to kind of take advantage of it. So
Okay.
it has to be
one
a hardware.
question. Yes.
Just, yeah, so one thing which machine learning, let me not call it AI or other things, are showing promise is solving complex optimization problems. So let's not talk about natural language processing or other things. And I assume a design, especially which goes from materials all the way to a full chip, is a massive complex optimization problem. What are your thoughts on, is there other possibilities available to find design points which are actually require just either large human effort or sometimes are just not being explored because such a large space to search from? Are there a design, essentially in design, there is, I assume, opportunities to go all the way from materials to circuits?
Yeah.
Yeah, please.
Yeah. I guess you're asking about, there has been a lot of work in analog based compute, right? Like people try to build SRAMs or MRAMs or DRAMs that can kind of take signals and accumulate using the current.
Talking about designing your chips. I'm just learning to design your chips better, not about what the chip does. So because I think, because that's a big layout is just a massive optimization problem, right?
Right.
So
Yeah, that's already happening,
Yeah,
right? You know,
but-
you
but
can see
especially
in the literature
Amazon.
there is a lot of work done to kind of, that's using more like the LLM types. The solvers are actually CNN and LLM type models, but they solve the optimization problem, right? So what they do, like NVIDIA has talked about this, Bill Daly has written a paper, I think. You can take all the existing designs, right? So they feed every design that's available into this and then ask it to review what you're trying to do and predict the optimal layout and things. So I think this is happening. It's progressing.
If you're asking, for example, us further down the chain where we're looking at, devices and optimization of implants and epitaxy, I have yet to see AI make any dent in there. I mean, it would be great for instance, you should try this different compound, gallium nitride with aluminum and nitrogen, and this would be better than what you got. That is not there yet. It still requires us to understand band theory, understand critical field breakdowns and why this works, and how would I synthesize this epitaxy, and how would I? So I have yet to see in any part of my field a contribution of AI. It's at a different level, not at that basic fundamental level. Still, you got to be a T-Rex and go out there and look at basic devices, understand band theory, understand epitaxy, understand all that stuff. But I'd love to see that, but I have yet to see it.
I think I can take one more question if somebody has. Nick?
So I guess my question to piggyback on that is, do we have enough T-Rexes that we can build the next 10 years of hardware without that leap in machine learning and AI?
I mean, as Ian Galton said, yes, a lot of people are going towards the softies like, CS and hardware and writing MATLAB code and not building anything. And I think the US is still okay because we have immigration and we do attract the greatest mind in the world to come here, which is, I always say the best thing that the US people have done is that they created a country where immigrants feel welcome to actually come here and shine and do their best, while many other places in the world didn't create such a system. But I can tell you, we are doing much, much better than in Germany. I mean, when I talk to my German colleagues at Ulm and Stuttgart, and you say how many people are doing hardware, and they say 0. I mean, they have no one in their RF microwave class, like not a single human being in their microwave classes, or RF classes, or VLSI classes, or things like that. So I would say, keep the US the way it is, and you can attract all the T-Rexes from all the rest of the world. Yes, from your neighbors in Canada and Mexico to as far away from India and China and everywhere. Yes.
This conversation stays here in this hall.
No,
Do I
I mean,
have-
it's a good system. It's a good system. It's a great system.
Thank you, all the panelists and all the audience of good questions.